Let me start by thanking the organizer for this for the invitation to speak in this very nice conference. I'm going to present a recent work which is joint with Yujin Kim, Eyal Lubetzky, Bastien Mallein, and Ofer Zeitouni, whose pictures are put there. And let me start by presenting briefly the model. So I imagine that everybody knows what I'm talking about, but just to be safe. So the branching Brownian motion in dimension D is a particle system where each particle performs a Brownian motion in R to the D. The particles are independent and they split at rate 1 into 2 particles each time. I'm just going to consider a simple case. And unless I say otherwise, I start with 1 particle at time 0, at position 0 at time 0. And so here you have a simulation in dimension 2, where the color corresponds to the age of the particle. So the red particle are the oldest, right? As time evolves, you have this growing cloud of particles. And those purple particles here are the particles that have appeared the most recently, and which obviously are also the furthest away from the origin. So in terms of notation, n of t is going to be the number of particles alive at time t. Okay, and of course this is n of t is just a pure burst process. Xi of t is going to be my notation for the position of particle I at time t. And I'm going to call Ri of t is going to be the modulus of particle I at time t, so the distance to 0. And theta I of t is going to be the direction of this particle. Okay, so it's a point on the unit sphere. Okay, is it clear? So, so what kind of questions are we interested in? So the first one, the obvious one, is how fast does this cloud grows? And so you might be interested in studying the maximal displacement. So R star t is the among all particles alive at time t, you look at the one which is the furthest away from 0, and the distance of this particle to 0 you call R star t. And there is so the very easy remark you can immediately make is that if you project your process, your BBM in dimension D, on one specific direction, okay, so here you have this black line, which is a direction I've chosen, and you project everything onto this line, well, that's just what you get then is just a standard one-dimensional BBM, right? So the maximal displacement in dimension D is going to be at least as large as the maximal displacement in dimension 1. And in fact, you can expect that maybe it's going to be larger. But, you would want to quantify how much larger. And the second obvious question you can ask is, okay, in which direction do you expect to see this maximal displacement? Let's call theta star of t the direction in which you will find the particle that has traveled the furthest away from 0 at time t. So what can you say about this direction? Well, at first sight, it might seem that you can't say much because, of course, your model is completely spherically symmetric, right? So so at any time t, the direction of the maximal displacement is going to be a uniform on the sphere, and that's it. But let's say now, instead of starting with one particle at time 0, at position 0 at time 0, I start at some non-zero position, say position small x here. Okay, so at large time, do you think that you will remember that you've started in this direction, and are you more likely to find your maximum displacement in this direction than say in this direction? So what do you think? Is it true that the distribution of theta star of t still converge to the uniform, which will mean that you forget this initial advantage, or will you remember this initial advantage forever? Okay, so let's see what happens. So to understand what happened in dimension D, I need to go back and tell you about the story of what happens in dimension 1. Okay, so I'm going to spend some time now telling you about all the results about the one-dimensional BBM. So the one-dimensional BBM is exactly the model I presented before, just in dimension 1. Particle branch at rate 1 into 2 particles. They move at they move as standard Brownian motions, and the particles are independent. And I'm just going to order the particle from topmost, x1 of t is the one here, to the lowest one, which is xnt of t. Okay, so the question you want to, type of question you want to ask is, where is this topmost or rightmost particle x1 of t, and what do you expect to see if you zoom around this position? Sorry, so this should not be here. Okay. So if you define, of course, there is this well-known fact that the branching Brownian motion is related to the Fisher KPP equation that we just heard about. So if you call u of x and t 1 minus the CDF of the position of the rightmost particle, of the maximal particle, okay, so it's the probability that x1 of t is above position small x. Then if you decompose on what happened at small times, it's easy to see that this function will solve the KPP equation, right? So dtu is half Laplacian u. So I have a half because I'm taking a standard Brownian motion, plus the reaction term, which is u1 minus u. And of course, the initial data is just the Heaviside function. Okay, so this was introduced in 1937. And it's a reaction diffusion equation. And it's models invasion phenomena and front propagations. So so I'm sure that you all know how the solutions of this question behave, but just let me remind that if you start with this Heaviside initial condition, you wait 1 unit of time, you're going to see something like this. 2 units of time, you're here, and this is after 5 units of time, 10 units of time, and 20 units of time. And what you see here is that it looks like you have this stable shape, which is moving to the right after some time at some constant, at some linear velocity. And this is indeed, the content of Bramson's celebrated papers in 78 and then 83, which tells you that if you look at your solution U around a well-chosen position that I'm going to call small mt, okay, u of mt plus x and t is going to converge uniformly to this limit shape. Okay, so here you should think of mt as the position of the front, and w of x is this shape you see here. And so the question is, what is mt? What is this magic position you should center by? And so in the original paper of KPP in 37, they were able to say that, well, if you take mt like something root 2t minus a correction that goes to infinity, that should be mt. And then Bramson was able to say that the correction is actually this celebrated minus 3/2 root 2 log t correction. So if you take mt like this, then you have this convergence. But if you choose, you could also choose mt to be the point where at time t this function u is equal to 1/2. So you cut at 1/2 and you look at this point, and that's your m1/2 t. Then it's going to have the same development. Then you have some constant here and a small o of 1 term. And this w, the shape to which you converge, of course, it's the critical traveling wave, as it's well known. And I'm saying the critical traveling wave because the solutions to this ODE are unique up to a horizontal shift. Okay, so this is kind of very classical. So for the probabilists, what this means is that you remember that u of x and t was 1 minus the CDF for the position of the maximal particle. And so because now we know that if you center by nt, u of nt plus xt converge to wx, well, that means that if you look at the variable x1t minus mt, so the maximal displacement, and you subtract this empty function here, then this will converge in distribution to a random variable, which I can call capital W. And 1 minus the CDF of capital W is given by omega, the traveling wave. Okay, so omega, the traveling wave, is related to the CDF of this limit distribution here. Okay. So so now we can. So I think this is all very, you probably, everybody knows this very well, but you can go a bit further and you can ask, okay, what does this convergence in distribution precisely mean? So it could mean, so let me try to argue here, it can mean two things. You could have a sort of ergodic, what I call some sort of an ergodic convergence, meaning that the position of the extremal particle is actually going to fluctuate around this deterministic mt. And in fact, if you ask, what is the proportion of time that x1, that the maximum displacement, spends above, say, ms plus x, and you ask about what is this proportion of time, then it should converge to, the ergodic thing would say that it will converge to, this proportion will converge to omega of x. Or you could have something a bit more like a convergence distribution, like what happens in polar urns, for instance, where you have a random quantity centered by mt, and it converges to a random variable, capital W, okay? And it's an almost sure convergence. Okay, and so the question is, which case are we here? And if you think a little bit about it, you will see that you are in neither of those. Okay, so in fact, if you do some a simulation and then you really cherry pick your simulation very well, you will get something like that. So this is a simulation which is due to Eric Brunet. So here in this simulation, you have your, so this black cloud here of particles is your BBM, and this pink line here is the position empty, small empty. And so what you see is that initially your particle is unlucky in the sense that it goes down very quickly and without branching for a long time. And so it builds up sort of a lag here, or an advantage if you want, that it will never catch up. Okay. And so after a while, now it starts to branch here around this point, and now you have, this cone shape, this growing cloud of particle, and you still have fluctuations at the boundary, of course. Okay, so if you zoom, you can see you still have those fluctuations, but you still have this initial lag that you never catch up. So you do not have this ergodic thing, but you don't have the almost sure convergence either. And so to understand what, so this was formalized or suggested in a famous result by Lally and Selke in '87. And what they showed is that, so the way they wrote it, was through this, through this double limit here. So you look at the probability that at time t, the maximal displacement is below, say, mt plus x, knowing fs. So fs is just the whole information up until time s in your branching process. And so if you let t go to infinity, so you should understand fs as the information about what happened at the beginning of the process, right? And then you let t go to infinity, and then s go to infinity, and then this probability converges to this random quantity here, which involves this z infinity guy, which is the limit of a certain martingale associated to your BBM. And so what this says is that if you observe your BBM long enough to have a good idea of what z infinity is, and z infinity converges quite quickly. Okay, so if you observe an initial time period so that you know what z infinity is, and knowing z infinity, then the distribution of x1, the maximum displacement minus m, is going to be a shifted Gumbel. Okay, so if you didn't, when you have something like e to the minus root 2x, that will be just that's the CDF or 1 minus the CDF that's the CDF of a Gumbel distribution. The fact that you put a constant in front, okay, it just shifts the Gumbel, because you can then put this through a log. You can put this in the argument and just shift the argument, right? So what this says is that the distribution, this limit distribution of the maximum displacement minus small m, it's actually a Gumbel distribution, okay, which is shifted by the limit of this martingale z infinity. Or more precisely, it's shifted by minus log of c z infinity divided by √2. Okay, and so the idea is that minus log, so this shift, this minus log c z infinity over √2, that's exactly this initial advantage, this initial lag that you've built up in the initial fluctuations, the early fluctuations of the process that you never catch up. And then the Gumbel fluctuations are those little fluctuations you see here. Okay, that's at least that's the picture which is suggested by Lally and Selke's result. Okay. Okay, so that's just exactly what I just told you. And so here the advantage, the initial lag or the initial advantage is never forgotten. But we can say much more than this. Okay, so we can say, so now is this other question I was mentioning, which is maybe you want to zoom around the position of the maximal displacement and you want to know what you see there. So to do that, what you can do is you can define, let's say, ET, script ET, which is the random point process of the particle position centered around this pink line, okay, centered by MT. And you can, and what you can show is that, and this was done about 10 years ago, independently by Arguin, Bovier, and Kissler, and by Elia Descon, myself, Eric Brunet, and Zanchi, is that this point process is going to converge to a limit object as t goes to infinity. Now, this limit object is what's called the shifted decorated Poisson point process, and I need to explain what that is. So, so let me, before focusing on what I wrote here, let me show you here how you construct such an object. So you start with a Poisson point process, and I'm going. So those red atoms here, those red dots on the real lines, are the atoms of a Poisson point process whose intensity is random and is given by c z infinity times e to the minus √2x dx. Okay, so this is a Poisson point process with this intensity conditionally on z infinity. And you see, because you have this e to the minus √2x intensity here, it means that there is a rightmost point, because e minus x is minus √2x is integrable to the right. Okay, so you have all those atoms, and those atoms, I'm going to call them the clan leaders for reasons that are going to become clear. Now, I'm going to decorate those atoms. So the way I decorate is I need an auxiliary or decoration point measure, which is the following. So what you do is you take a BBM and you condition it to have a large deviation, a large displacement event. So remember, your rightmost particle want to be around position MT, which is √2t minus 3 over 2 √2 log t. But now I'm going just to condition on the event that the rightmost particle is actually to the right of √2 times t. That means that I condition on the event that the maximum displacement is 3 over 2 √2 log t unit of distance too much to the right. Okay, so it's a large displacement, not that large, but it's large. And the decoration is just the position of all the particles that have branched off x1 of t as this particle was getting there. Okay, so maybe here you have a little branching event which has created those two descendants at time t. Okay, and you get the collection of all those positions plus x1 of t, and that's as t goes to infinity, you can show that this has a limit distribution actually seen from x1 of t. Okay, so you look at the sum of the Dirac mass of the position of the particle centered by x1 of t, conditional on x1 of t bigger than root 2 times t. This has a limit in distribution that you call d, and that's your decoration. Okay? And what you do is you take each of your clan leaders, which have now given different colors, red, purple, green, and so on, and you decorate it with an independent copy of this decoration measure. Okay? And then you superpose everything, and that's your limit point process E. Okay? So why do you call them the clan leaders? And why should you expect this picture? Well, it's because those clan leaders are, if you look at a particle alive at time t, and you look at all the particles that have a most recent common ancestor with this particle before time t/2 in the past. Okay. So, for instance, if I look at this red particle, I can look at all the other particles which have branched off this red path less than t/2 units of time in the past, right? And I'm going all those particles which are still alive at time t. I'm going to call them the clan of this particle, of this red particle. And the clan leaders are simply the particles which are the rightmost within their clan, okay, within their immediate family. And so what we're saying is that the clan leaders, so all the particles which are, the rightmost amongst their cousins, say, they are the clan leaders, and they form the Poisson point process with intensity E minus root 2x. And then you need to add up all the other particles which you have forgotten, and that's those particles here, and they form the decoration. Okay. Okay, so that's this interesting structure of the extremal point process in dimension 1. So now let's go back to dimension 2. So, so as I was saying, it's important to remember that if you take any vector u on the unit sphere and you project on the line which corresponds to this vector, you get back a one-dimensional BBM. Okay, so let's go back to my two questions. The first question was, how fast does the cloud grows? So where, what is the maximal displacement R star of t? And in 2015, Mallein proved that it's going to be near a position which is root 2t plus d minus 4 over 2 root 2 log t, right? So this, if you take d equal 1, you see that you recover your minus 3 over 2 root 2 log t. But now you have you see that the larger d is, and the larger this quantity is going to be, right? So larger dimension, as I was saying, is going to help you go faster. And what he showed is that if you center R star of t by this quantity mtd, then you get a tight sequence. And last year, Yujin Kim, Eyal Lubetzky, and Ofer Zeitouni proved that actually R star d minus mtd converge in distribution. You have convergence in distribution to a shifted gumball, exactly like we had in one dimension, except in that in their case, so for the one-dimensional case, the shift was related to z infinity, which is a function of the BBM itself. It's measurable with respect to the BBM. And in their results, they have a shift which is not a measure. They don't have a shift which is a function of the BBM. It's just some random variable. Okay, so we know the answer for we have you can use this as the higher dimensional equivalent of a Branton result, if you want. So so the second question was, in which direction are you going to find this maximal displacement conditionally on Fs, conditionally on what you observe at small times? Okay, so we want to do some sort of an analogy with a one-dimensional case. And so let me introduce zt of theta, which is the derivative martingale. Okay, so this is the same quantity I had in one dimension for the BBM you obtain by projecting everything on direction theta, right? So just multiply every position by taking its inner product with theta. So this is you can call this a derivative martingale in direction theta. And for fixed theta, there's no problem. This martingale almost surely has a limit, which is positive almost surely. And as you remember, this z infinity is related to the lag, to this lag that you never forget. And it's not hard to see that R star t wants to be in a direction where, at least the typo is not z infinity, it wants to be in a direction where minus log c z infinity is large. That's what it wants to do, right? Because you remember that minus log c z infinity over root 2 was my lag that I never forget. And so you want to be, it makes sense that you will more often find your maximal displacement in the direction where this quantity is large. So the question is, can we define a random measure mu on the sphere, on the unit sphere, which will have some sort of intensity z infinity of theta d theta? And the problem here is that, in fact, you cannot, z infinity theta exists almost surely in a fixed direction theta, but it does not exist almost surely for all direction theta simultaneously. Okay, so you have a problem because you could ensure that z infinity theta exists for all theta in a countable set simultaneously, but not for all theta. And here, so this is a simulation that Bastien did of the BBN in dimension 2 at 2 different times. So the times are, the orange particles are at smaller time and the blue particles are at a later time. And what I've plotted here, this green line, is MTD minus log CZT of theta. Okay, and you see that it looks like you have some direction, like this one, for instance, where indeed this advantage is bigger, and you tend to find a particle which are further away from zero in this direction. Okay, so it looks like still you should be able to do something. So that was exactly what our objective in the paper that we wrote with Bastien Mallein and Roman Stasinski. And what we proved there is that yes, you cannot define that infinity. You cannot define the limit of the derivative martingale in all the direction theta simultaneously, but you can find there is a random set of full measure in which z infinity theta exists almost surely for all theta in this set. Okay, so almost surely z infinity theta exists for almost every theta, if you want, on the sphere. And that means that you can think of this z infinity as as a weak limit. So it's going to be a measure on the unit sphere. Okay. How much time do you have? 2 more minutes. Okay, and by putting together, Yujin, so Kim, Lubetzky, and Zeitouni's proof of the convergence in distribution, and our proof, this result that there exists this z infinity theta exists for almost every theta simultaneously, we were indeed able to answer this second question. And you can prove, for instance, that if you take some set of direction, measurable set of direction A on the unit sphere, and you ask, okay, given what I observed initially in my BBM until time S, say, what is the probability that this maximal displacement direction will be in this A set? So maybe you can think of A as being, I don't know, the set of direction to the right. Okay, so what is this more likely that you will find your maximum direction to the right than to the left? Well, this converge, if you take first the limit in t to infinity, then s to infinity, a bit like in Mallein-Selke, this will converge to the measure, this z infinity measure of the set A. Okay, And in fact, you can also be much more precise than that. You can do the analog of what's been done in dimension 1 and describe completely the extremal point process of the BBM in dimension D. So let me call so ET here, script ET, is going to be a point process, but now I'm going to record both the direction on the sphere and the modulus. Okay, well, actually not the modulus, but the centered modulus. So really R. Okay, it's the point. This is the sum of the Dirac mass at theta I of t, the direction of particle I at time t, and of the center distance to 0, RIT minus MT. The limit object, my candidate limit object, so the end result is that this converges to something, okay? And the limit is script E. So what is this limit object E? Well, it's again a shifted decorated Poisson point process, exactly like in one dimension, okay? Except that now I have Dirac mass in theta I and xi plus y. So now my Poisson point process, the Klein leaders, they have two components, the theta I, and so they are theta xi are the atoms of a Poisson point process with intensity z infinity of theta, sigma d theta. Here, sigma d theta is a surface measure. Time, so there's some constant here which depend on dimension. And again, you recover this e minus root 2x dx Poisson point process for the distance. Okay, so you have this. Okay, so you can factorize this measure intensity between the part for the direction and the part for the distance to 0. And the decoration. So this is the Klein leaders, and you remember that you need the Klein leaders, and then you need the decoration. And the decoration are IID copies of the one-dimensional decoration. And you see that the decoration only affects the distance to 0. There is no decoration on the direction, and that's because I mean that's not surprising because you're looking at the limits in t to tend to infinity. So maybe at a very large time you have one Klein leaders which is here, and this is a very large distance. And now you're putting the decoration. So the decoration are, you remember, are the particles that have branched recently. So you have like a cluster of points around your Klein leaders. But of course, because this distance here is very large, distance grows linearly with t, the angle between those blue points and the red points tend to 0. And so there is no decorations on the angles. I hope this makes sense. Okay, so I think, do I have a couple more minutes? I think I start a little bit later.
Yes, 2 more minutes.
Okay, good. So let me just give very briefly 3 ideas maybe of the proof. So essentially, we work by proving convergence of the Laplace transforms by finding where are the particles which are actually important that contribute to this ZT martingale, and by then localization of the path of the external particles and showing that we have stabilization of the angular process. So I'm not going to say much about this. Okay, so I just need to say, okay, so in fact, okay, so we introduce this weight of the particle Wi, which is almost the weight that you get in the derivative martingale, except that we pre-multiply by this polynomial term in the distance to 0. And this is really one of the important arguments in Eyal, Yujin, and Ofer's paper, is that if they look at MT, which is the sum of those weights for the particles which are in this Goldilocks like region, then it's not quite a martingale, but still it's going to converge to something, to M infinity. And that's in distribution, and that's the shift they get for the position of the maximal displacement. And what we show is that actually, if you take any continuous function and you sum f of the direction theta I by this weight, then you will converge to our measures at infinity integrated against f. And so that means that there M infinity is actually our measure Z infinity of the whole sphere up to a constant, a multiplicative constant. And the second thing we have is that we have those path localization arguments, which say that if you take any particle above, say, position mt plus y at time t, okay, then at a large time L, but much smaller than t, then this particle must be in the Goldilocks region. It has to be in this, what I call I win here, interval win, which is this Goldilocks region, meaning that you have to be between √2 times t minus t to the 2/3 and minus t to the 1/3. Okay, so you have some other properties which I'm not going to detail here. The third argument, which is the one which I always struggle the most to explain, and I have no time now to do it probably here, but it's a really, really cute argument. It's a purely geometrical argument. And what it says is following. So the radial part, of course, this I of t is the modulus of a Brownian motion in dimension d. And we know that this is a d-dimensional Bessel process, which solve this SD, right? Now, conditionally on RT, theta t is going to be a Brownian, is going to be a diffusion on the sphere, whose diffusion constant at time t is going to be RT to the minus 2. But because RT is a Bessel, RT is growing, and so the diffusion here is going to 0. The diffusivity constant is going to 0, and so in fact theta t is going to converge almost surely. And one way we explore this is we say, okay, we know that all the particles which are going to be leaders at time t, because of what I said in the previous slides, they're going to be already at a large distance from 0 at time L, capital L, which is large but small compared to it. And so what you want a particle which is a leader, which is above mt plus y. And to be above mt plus y, a descendant of this red particle here has to be outside of the black circle here. But you also know that it cannot go too far because of Bastien's result, for instance. It has to be in the red circle. So the fact that you have to be outside of the black circle and inside of the red circle means you need to be in this very little crescent here, this sliver of a crescent here. And as t goes to infinity and L goes to infinity, this crescent becomes smaller and smaller, and in fact this angle here goes to 0. And what that means is that the descendant of a particle which is far away at time L is going to be almost in the same direction at a much larger time t in the future. And that's an important point for us. And I'm going to stop here because I'm out of time. Thank you.
Thank you. So any question from our audience? So if I'll ask them a naive question. So if we look at the Brownian branching motion process, if we look at the median of the particle, so where they are, so this is correspond to the Bremsen's shift, right?
Yes.
And then if and here you're looking at the leader at the furthest particle, and then so is there a way to characterize how far you move in between the median and the furthest particle that you stay in the Bremsen's regime, and then so is it like
so Bremsen's MT is the median of the position of the extremal particle, right? So this is the same thing. Both Bremsen and here we're looking at the extremal particle, the one which is the furthest away. So in Bremsen, so in one dimension I was saying the one which is the furthest to the right, but you could also say the furthest away from 0. That's the same thing.
So if it is in proportion, so if I look at the 1/3 of the one-third quartile or any proportion, it will be still in the Bremsen, right? But if we look at some
the 1/3 quartile, because you have the convergence to this shape, right? So if you this is okay. So let me answer for one dimension because this is the same thing. So you see the half quartile is here, the 1/3 quartile is here, and or here, and so what happens is that the difference between the median and the third quartile converge to a limit which corresponds to the shape of this traveling wave.
Yes, but when n is large, if I look at the square root of n or something like that, so it's not proportional anymore. So is there any like results that we're going?
What is n here?
Like n is the number of particles at time t.
But that doesn't. Okay, the point is that's the point, right? This is about the CDF of the extremal particle. It doesn't, as n goes to, this is as n goes to infinity.
Je n'ai pas bien compris. Pourriez-vous répéter votre
This is as n goes to infinity. Yeah, Siri thinks I talk to her when I speak English for some reason.
Okay, thank you. Is there any other question for our speaker?
Yeah, hello. I'm going to try a question. It might be disastrous because a lot of the talk was a bit too hard for me, but I understood that what you end up seeing is that the anisotropy of the distribution is reflecting some anisotropy that occurred in the initial stages of the process.
Yes.
And so it made me think that maybe is there like some particular signatures when a pattern is coming from contingency and is not, you know what I mean? Like that the fact that we see some anisotropy really comes from far in the past events, versus that the pattern actually reflects something more structural. I mean, I realize it's a bit esoterical, my question, but.
Okay, let me. I'm not sure. I hope I understood correctly. So, but correct me if I'm wrong. Okay, but I think that's okay. So what I'm saying is that if you ask me at a large time t, I don't know anything, but you ask me, can you guess at a large time t in which direction you're more likely to find let's say this theta star direction, the maximal displacement? Well, it's uniform on the sphere at all time t, so I cannot make a good guess. But if I observe actually a realization of my process on a long time, I will see that the direction, this theta star direction, will fluctuate between at what time it will be north direction, then later more to the east, and later, but it will tend to be more often in certain directions. Okay, and so for instance, in this simulation here, you see that there will be time where the maximal displacement is not going to be in this direction, right? Maybe at some times, by chance, I will see the maximal displacement in the north direction. But the proportion of times in which it will be in this direction is going to be superior. It's going to be greater. Okay, and this is due to one of these early, or very old contingencies, as you said, I think. Whereas,
I think you confirmed that I understood at least a little bit, so I'm already happy about that. And I don't think I had anything profound to ask. In fact, I was just trying to make sure I understood. So thanks.
Yeah, no problem.
Okay, so let's thank our speaker again.